mission will start with our launch, and in that we'll have everything we need to go to Mars.
We're going to launch in a relatively conventional rocket, but at the top of that rocket is going to be a cruise stage and the re-entry vehicle to get us landed onto Mars.
There'd be a short, ever such short burn to get us away from the Earth and into this curved trajectory going towards Mars. During that, our spaceship will literally just split apart, connected by our little tether, and it will start spinning to create this artificial gravity. Fingers crossed there won't be any solar storms on the way from the Earth to Mars, and we can keep going nice and gently. Once we get to Mars, we'll re-tether it together, the astronauts will join in the nose cone, and it will be ejected into the Martian atmosphere. This is why you need this big cone at the front to soak up all that heat going through the atmosphere.
At 700 miles an hour or so, they will be able to release a parachute. Right at the last moment on entry, the legs are going to be deployed, and we hope that re-entry vehicle quite gracefully descends on those retro rockets down to the surface of Mars.
Some people think that the use of humans is just something that is popular and very attractive from an adventure and inspirational point of view, but there are also real scientific benefits for sending humans. Humans can data process while they're walking around, while they're looking at rocks. They're probably the most sophisticated computer, the most sophisticated robotic living organism that we can imagine.
There'll be the building of the habitat, and there'll be some experiments on the Martian surface. After a couple of months, we'll drive from our landing zone to the return launcher. We'll getting that, hopefully it will be fueled up, fire off from the Martian surface and fly back to the Earth again.
So we're on a merry-go-round today to demonstrate how we could use centrifugal forces to generate a form of artificial gravity that will keep our astronauts healthy and in the right kind of shape for when they land on Mars. So this is our homemade astronaut, as you can see. He's made out of a plastic bottle and a bit of tape here and there. We're going to use him to see how the fluids can shift through the body when you apply different gravitational forces. And you'll be able to see how the fluids shift towards the feet as the merry-go-round spins faster and faster. The problem is, we live on Earth, where there's gravity at all times. But when you're in space and you're experiencing weightlessness, suddenly your bones and your muscles no longer have the forces on them they normally experience, and they waste away. A bit like if you lie in bed all the time. So for our design, we've decided to split the spacecraft up into two parts, and they'll be attached by a tether. These two parts will then spin around each other, and that will generate centrifugal forces that will generate this artificial gravity for us.
You turn your spacecraft into effectively a roundabout, spinning round a point, the nose cone and the living quarter, and as it's spinning round, it creates an artificial gravity field inside.
Yeah.
Orientation, and that's a factor of 3.
So we've obviously got some real issues with a long-term mission in terms of the deconditioning that goes on in the space environment. Bone loss, for example, is around 1 to 2% per month, and if they're landing, they'll be susceptible to fractures, for instance, if they've got to be exerting themselves.
Well, you see that with the International Space Station.
Already,
right?
they're already
they have to be
them up
carried
for-
out after 6 months in that microgravity.
Muscle loss, neurovestibular function goes in microgravity as well. But luckily, we've got quite a nice system with our rotating spacecraft design.
So once we get out of Earth orbit, we're ready to go into our cruise configuration. So the first step is to get all of the humans out of the re-entry vehicle where they would be during launch into the cruise module. Once they're in there, the re-entry vehicle separates away and it goes out by a few tens of meters. At which point the thrusters on both the cruise vehicle and the re-entry vehicle are used to set them in rotation around each other. And that will speed up until we attain an artificial gravity equivalent to Earth's.
Manager on EDL Ops.
EDLCom, this is Dynamics on EDL Ops.
Go ahead, Dynamics.
So welcome to our virtual spacecraft. This is a mock-up of the real thing, and at the moment, as you can see, we're in a weightless environment. That means we've just taken off of Earth and we're in Earth orbit at the moment. We actually started our journey all the way back there that used to be up. That's where we set off from inside the rocket. My colleague, Dr. Simon Foster, is working over there. He's monitoring stuff we have on all the computer screens so we can track what's going on at Earth and keep contact with the ground crew over there. And everything that we need for this 9-month journey has to be contained within this environment. We have to be fully self-sustaining because there's nothing else that we can get.
So here I am, I'm monitoring the life support systems, basically making sure we've got enough oxygen, that the system's still intact, the craft hasn't been breached in any way. The other thing is we're looking where we're going, basically, making sure there's no solar flares, anything like that on our way which could prove a danger. We're going to start rotating soon, pull the system apart and get the artificial gravity going. Now, we've got to make sure everything is working. Otherwise, once we get out into space, there's going to be no coming back. So we have to make sure all the systems are ready to make sure we are safe.
Go ahead, Dynamics.
Is our display configured correctly for you?
So the spin cycle of the spacecraft is now fully engaged, and that's why I am standing. We are simulating the Earth's gravity through spinning the spacecraft, and this is how we're going to spend the 9-month trip to Mars, as if we were stood on Earth, but actually in artificial gravity.
So the vehicle here for the next 9 months is going to be our home. So it's actually quite spacious, unusually for a spacecraft actually, because everyone's usually hemmed in. And there's probably quite a good reason for that, because as I say, for 9 months, we're going to be living here. We're going to have to get used to each other. We probably want some of our own space occasionally.
This is our water supply the whole way. It's actually recycled urine as the water that we're drinking, because it would be inconceivable to take all the water we need for the whole way and also just store all of that waste. So this is what I'm drinking on the journey.
All along our journey, our vital statistics are going to be monitored, but occasionally someone will get ill. Up here, we're going to have to solve this. Now, each of us is going to have medical training, and today, unfortunately, Martin's feeling ill. Now, he's been feeling some chest pains. Now, that could just be down to the food rations. They aren't particularly nice, but it could be a problem with his heart, because this is one of the issues we've got to look out for. So I'm going to check Martin out, make sure his heart's working fine, and then therefore we can eliminate that problem and know it's probably just the rations. More than the actual launch, which was pretty dangerous, the biggest fear I have, and probably everyone in the crew has got, is going to be solar radiation. Occasionally we could get these things called coronal mass ejections. One of these could hit this craft, and the long-term impacts could be increased risk of cancer. Now that is going to be, for all of us on board, a real risk. You know, it's going to keep us awake at night.
Man, tones. Very nice picture. And we're expecting tone start at 5:13:17 UTC.
Copy.
So what you're seeing behind me is the sun. It probably looks a bit different from how you see it from everyday life, but this is just in different wavelengths of light. And it shows us more about what the sun actually does and the stuff that it throws at us all the time, called the solar wind, and the structures you get in that, solar flares or coronal mass ejections, things like that.
Think of a gun firing a bullet. It's not the flash that's going to kill you, it's the bullet. A solar flare is like the flash of the bullet being launched off, and the bullet is this coronal mass ejection. It's all these really high energy particles that's going off. If you get hit with one of them, you gotta look at severe radiation sickness or just death, really.
The really high energy particles will just go straight through.
Cosmic radiation, we call them galactic cosmic rays, and basically they come from all stars and exploding stars, and they're constantly firing out particles towards us.
We've got some great results off of the Mars Curiosity rover. On its trip to Mars, it measured the radiation from these galactic cosmic rays, and it was exposed to quite a lot, actually surprisingly more than some might have thought. About 2/3 of the level that NASA is prepared to risk over the whole of an astronaut's life. just on the way there and back again.
We have on Earth space weather forecasters. They know when a solar flare is likely to happen, and the solar flare is associated with a larger amount of radiation coming from the sun. Once the crew get warning of this, they will reconfigure the vehicles. They'll pull in the re-entry vehicle on its tethers, and they'll put as much mass as they can between them and the sun. The re-entry vehicle will sit between them and the sun. They'll reorient the cruise stage so that all of the stores, all of the waste that is on board is between them and the sun as well.
We might even like to take a hint from the Earth itself. It's got this magnetic shield around us called the magnetosphere. Why don't we do something a bit similar to that ourselves? You know, we've got the LHC has superconducting magnets to keep energetic particles in. Why don't we do it the other way round? Have a LHC the other way out, where we're trying to keep those energetic particles away from us.
When we get to Mars, obviously there's problems there with radiation as well. The atmosphere is different, so we might get exposed to more of these galactic cosmic rays and also particles coming from the sun. So one of the options for habitat is actually digging down into the Mars surface and building our habitat in that and using the rock as a natural shield. An easier thing to do was probably to put our habitat down and then actually go out with shovels and just cover the habitat in dirt from the Martian surface. Just that dirt would provide a really good radiation shield, and that's what the astronauts are going to have to do. We're going to have to use what's on Mars. We can't take stuff with us. We're here to test out our parachutes for landing on the Martian surface, and so the best place to try this is here at the Queen's Tower. So let's have a go with one parachute and fingers crossed this is going to work. So land it out and away we go. So what we're going to do now is add more parachutes to see if that has any effect at slowing down the lander anymore.
So when we get to Mars, the crew moves into the re-entry vehicle, and at that point they're ready for the entry, descent and landing onto the surface of Mars. They'll essentially be coming into the surface of Mars at around 14,000 miles per hour. Most of the energy is going to be lost by the front end, the thermal shield of the re-entry vehicle, and as that heats up and it absorbs the energy of re-entry, the spacecraft will slow down. At 700 miles an hour or so, they will be able to release a parachute.
Shoot them out and they'll slow things down for us. But the problem is that might not provide enough resistance to slow our module down. So we're also going to have to use retro rockets, and these are just rockets placed underneath, like glorified fireworks basically, to slow us down to get a soft enough landing.
Right at the last moment on entry, the legs are going to be deployed, the retro rockets fire up, and we hope that re-entry vehicle quite gracefully descends on those retro rockets down to the surface of Mars.
And this is all to do with the fact that the Martian atmosphere just isn't like anything on Earth. This is vastly different. You can't take chances. If you lose human beings, this is going to be a massive disaster. So we've got to make sure as much as possible we get them down safely.
So this may look like Mars, but in fact this is a location on Earth, and it's a particular environment that has similarities to the Martian environment. And so it's a very good place to come and consider what it might be like to send humans to Mars. If you're a human being on the surface of Mars, you can look around, you can spot rocks, you can think about what they look like, take a step to the right, take a step to the left, look in the shadows, maybe tap them with a geological hammer and get some extra information. and immediately process it using your brain. So far, most of our exploration on the Martian surface has been done by robots, and robots provide a certain level of information, but it's usually quite prescribed, and so we have to sort of know what we're going to do before we get there. If you send human beings to Mars, then human beings can really react to the information that they're receiving. So one of the interesting things on Mars is the difference between the rocks and the dust. So the rocks represent local materials, but dust is material that's been abraded, swept up into the atmosphere and distributed around the globe. So one sample of dust on any point of Mars contains a great deal of global information. And from a human exploration point of view, dust is very important. Dust gets everywhere. It gets in your suit, it gets in your breathing apparatus, and it could be toxic. So when we send humans to Mars, we can be pretty sure there's life on the red planet because we'll have took it there. But one of the great questions is, has life existed on Mars in the past? How we detect life or evidence of past life on Mars is a difficult question. What is the best way to actually go about finding information that's in a form that we don't currently know how it's going to look? If you send a human to Mars, then that human can really make decisions on the spot. They can follow leads like a good detective. And that is something that's quite unique to human exploration.
So what we're going to do is go through the various stages that will be needed to make fuel on the Martian surface. Now firstly, I've taken a tray full of ice and covered it in sand, basically to represent the Martian geology. And if you look at a picture of Mars, you should be able to see that there's ice caps at the top, and this is solid ice, water, and also solid carbon dioxide. Now what we can do is we can drill down on our astronaut's wheel to get this solid ice and turn it into liquid. Now to do this, I'm basically going to take a screwdriver, heat it up, go down, melt this ice by burrowing through our Martian surface that we've got here, and basically I'm going to turn that frozen water into liquid water and steam, which we can then collect. Now once I've collected this liquid water, you'll see that I'm going to place it into a bowl. Liquid water is H2O. Now we can use electricity for a process called electrolysis to pull the hydrogen and the oxygen apart. And I'm going to do this by simply dropping a 9-volt battery into our bowl of water. Now what you can see happening here is on the negative terminal, which is the fatter terminal, you should be able to see bubbles forming. And that's hydrogen gas being formed out of the water. Now we can collect this hydrogen gas and the oxygen gas being formed to create fuel or use it as fuel. And this is what we're going to do in the third stage. So I've collected this hydrogen gas that's been made and I've filled a balloon up with it, which you can see here, and you can see it floating around in this box. Now I'm going to take it away and put it on the stool here. So hopefully this balloon is full of hydrogen gas. We're going to react it with the oxygen in the atmosphere that we're breathing in. Now on Mars, there's not going to be any oxygen in the atmosphere, so we're going to have to use the oxygen that we've created from the electrolysis for this reaction. But here on Earth, we can simply use the oxygen in the atmosphere. So I'm going to light my splint and get back. Now you should be able to see that as I light the splint and getting closer, there should be a nice explosion, and that's the hydrogen gas reacting with the oxygen, and it's recombining to make water again, but it's giving out lots of energy. Now, we may not want to use this as fuel. Instead, what we might do is create methane. So we'll take that hydrogen and react it with the carbon dioxide that's already in the atmosphere to create methane, which is CH4, and that's 1 part carbon, 4 parts hydrogen. The reason we want to do that is basically methane will give us a bigger thrust. And so we react the methane with the oxygen we've created from the water and hopefully use it in our engines to blast off from the surface of Mars with our astronauts inside the rocket.
getting them to Mars. That is actually relatively easy. The big difficulty is getting them back again. To get humans back from Mars, we need to get a rocket onto the surface of Mars. And that's the tricky part of the entire mission. We not only have to get the rocket, we have to get the fuel for the rocket. And that's probably the largest proportion of the mass. So we're not going to take it all the way from Earth. In fact, we're going to produce the fuel on the surface of Mars. So our ascent vehicle, what's going to get us off the surface of Mars, is going to be taken up in a previous launch alongside a factory which is going to fill it full of fuel. And those are going to sit on the surface of Mars where we know there is ice, where the factory is also going to do some mining. It's going to dig up water which is just below the surface, and it's going to combine that with the carbon dioxide in the atmosphere to fuel up the tanks ready for the return to Earth. Now, we have a problem. Mars is generally a very inhospitable place. The least inhospitable areas of Mars are around the equator. On a warm day on the equator, it gets to just about freezing. So it's in that area that we would like to land. But what we want is a lot of rocket fuel from the water which is closer to the polar regions of Mars. So if we look at this northern ice cap, this is the ice that we knew about for some decades. What we didn't know is that underneath this top third of Mars is water ice just below the surface. And so we will have put our return vehicle and the propellant factory probably around this region of Mars. Still a long way for where we might be landing nearer the equator. So we've got to make quite a road trip of about 1,000 kilometers across the surface of Mars.
Well, when you're thinking about landing on Mars, the easiest place to land is near the equator. But if you want to set down a craft which makes use of liquid water to generate a propellant, then liquid water has to be generated from ice, and that ice is above 40 degrees in latitude. So you've got a sort of tension there between where you would like to land safely and where you would like to tap into your resources. And so the more north you go, or the more south you go on Mars, the more chance you have of finding this frozen water that's going to help to produce your propellant. So there would be a possibility of driving an extended period of time or an extended distance across the Martian surface.
Now, in some ways, this could pose a problem. It's like having a moon buggy and driving across, and it's going to be a bit of a road trip for the guys. But in other ways, we could see it as an opportunity, because actually we could do it. This will be the first time that anything has actually travelled geographically across a vast surface like this. We'd be able to go in a line and actually look at how the rocks change. And that's really interesting. You know, we might see get samples of rocks from different areas, might be able to look for life.
So once they get to the ascent vehicle, they will go through a very careful health check before they climb into the ascent vehicle, ready to get back into orbit. And then they will have a chance, of course, to say one last goodbye to Mars, and then they'll be ready for the final countdown and taking off from the surface of Mars. It will look a little like a slow motion launch from the surface of Earth. But the amount of power generated is going to be quite considerable. And that is where this year's production of fuel will be burnt in a very short period of time.